Hello, and welcome to Eternal Education Network, the channel where curiosity meets the wonders of the universe. Here, we dive deep into the mysteries of science, unravel the secrets of space and time, and explore ideas that expand your mind and ignite your imagination. If you're someone who loves learning, questioning the unknown, and discovering the hidden truths of our reality, this is your new home. Today, we're embarking on an extraordinary journey into the fabric of time itself. Is time real, or is it an illusion crafted by our minds? How does quantum physics and Einstein's relativity redefine our understanding of time? Stick with us as we break down these fascinating ideas in a way that's not just educational, but thrilling. Before we jump into this mind-expanding adventure, make sure to like this video, share it with your fellow knowledge seekers, and hit subscribe to join the Eternal Education Network community. And don't forget to turn on notifications so you never miss our next deep dive into the universe's greatest mysteries. Let's journey beyond what we know and discover what it means to truly understand the cosmos. Let's begin. Time. It governs the rhythm of our lives, defines change, and shapes the universe in ways both wondrous and profound. We wake up to clocks ticking, measure progress in years, and observe celestial bodies move through space, forming the tapestry of past, present, and future. But have you ever wondered, what is time truly? Is it a fundamental property of the universe, or is it merely an illusion, a mental construct invented by humanity? From the enigmatic depths of quantum physics to the grand cosmic framework of Einstein's theory of relativity, the nature of time challenges our perceptions and stretches the limits of human understanding. Albert Einstein's theory of relativity fundamentally altered our understanding of time and space. In his 1905 special theory of relativity, Einstein introduced the concept of SpaceTime, a four-dimensional fabric where space and time are interwoven. One of the theory's most astounding revelations is that time is not a universal constant. Instead, it can stretch and compress depending on factors like velocity and gravitational fields. Time dilation, slowing down the clock. One of the most famous implications of relativity is time dilation. When an object moves at speeds approaching the speed of light, time for that object slows down relative to an outside observer. This phenomenon, confirmed through experiments involving atomic clocks on fast-moving jets, suggests that time is malleable. For instance, consider the thought experiment known as the twin paradox. One twin travels on a spacecraft at near light speed, while the other stays on Earth. When the traveling twin returns, they are younger than their sibling. The explanation lies in time dilation. The traveling twin's clock ran slower due to their high velocity. Time, it seems, is not an immutable constant, but a variable linked to motion. General relativity, gravity's grip on time. Einstein's general theory of relativity, published in 1915, extended these ideas by showing that gravity can also warp time. Massive objects like planets, stars, and black holes bend space-time, creating what we perceive as gravity. This warping affects the flow of time, making it run slower in stronger gravitational fields. One striking example is the gravitational time dilation experienced near black holes. In the movie Interstellar, the characters experience an hour on a planet near a supermassive black hole, while 7 years pass for those farther away. While dramatized, this scenario accurately reflects the profound influence of gravity on time. Through relativity, time is revealed not as a fixed backdrop, but as a dynamic, flexible dimension shaped by the universe's structure. While relativity revolutionized our understanding of time on cosmic scales, quantum physics raises questions about its nature at the smallest scales of reality. In the quantum realm, where particles behave in ways that defy classical intuition, time takes on an even stranger character. The problem of time in quantum mechanics. In classical physics, time is a parameter that flows uniformly, allowing us to track the evolution of systems. But in quantum mechanics, the role of time becomes ambiguous. The famous Schrödinger equation, which describes the evolution of quantum states, treats time as an external parameter, not something intrinsic to the system. Moreover, attempts to reconcile quantum mechanics with general relativity face the problem of time. In relativity, space-time is a dynamic entity that interacts with matter and energy. In quantum mechanics, time is static and universal, creating a fundamental mismatch. This disconnect has profound implications for our understanding of reality. Quantum entanglement and non-locality. Quantum entanglement adds another layer of mystery to time. When two particles become entangled, their states are linked in such a way that measuring one instantly determines the state of the other, no matter how far apart they are. This instantaneous connection appears to transcend the limits imposed by the speed of light, challenging our conventional notions of time and causality. Experiments confirming entanglement suggest that time, as we experience it, may not govern the deepest levels of reality. Instead, quantum processes might operate outside our familiar timeline, hinting at a more fundamental framework where time is emergent rather than fundamental. One of the greatest puzzles in physics is the arrow of time. Why does time seem to flow in one direction, from past to future? This question is deeply tied to the concept of entropy, a measure of disorder in a system. Entropy and the second law of thermodynamics. The second law of thermodynamics states that entropy in a closed system tends to increase over time. This principle explains many natural processes: ice melting, stars burning out, and the spreading of gases. The increase in entropy gives time its apparent direction, creating the distinction between past and future. However, at the microscopic level, the laws of physics are time symmetric. They work the same way forward or backward in time. This raises the question: why does entropy increase, and why does it give rise to our perception of a flowing time, the cosmic arrow of time? Some physicists argue that the arrow of time is linked to the universe's initial conditions. At the moment of the Big Bang, the universe was in an extremely low entropy state. As the universe expands, entropy increases, driving the forward flow of time. But this explanation raises deeper questions. Why was the universe born in such a highly ordered state? And does time itself have a beginning? The idea that time might be an illusion has captivated thinkers for centuries. In the 20th century, physicist Julian Barber argued that time is not a fundamental aspect of reality, but an emergent phenomenon arising from change. In his view, the universe is a collection of nows, snapshots of reality that exist independently of any flow. Similarly, the block universe interpretation of relativity suggests that past, present, and future all coexist in a four-dimensional space-time block. From this perspective, the passage of time is an illusion. What we perceive as now is just our subjective experience moving through the block. Time slows down at high speeds. Astronauts on the International Space Station age slightly slower than people on Earth due to time dilation effects caused by their high velocity and weaker gravity. Near the event horizon of a black hole, time slows to a crawl relative to distant observers. If you could hover near a black hole, billions of years might pass in the universe, while only seconds elapse for you. Some interpretations of quantum mechanics suggest that at the most fundamental level, the universe is timeless, with time emerging as a macroscopic phenomenon. The age of the universe, approximately 13.8 billion years, is measured by observing the cosmic microwave background radiation, the faint afterglow of the Big Bang. Certain particle interactions in quantum physics appear to work identically whether time flows forward or backward, challenging our intuitive understanding of causality. Ultimately, time is both a mystery and a tool. It is a measure of change, a dimension intertwined with space, and a concept that shapes our understanding of the cosmos. Whether time is real or an illusion depends on the framework we use to study it. In relativity, time is a dynamic entity shaped by gravity and motion. In quantum physics, it is a parameter with an uncertain role. Philosophically, it may be an emergent property or a construct of human consciousness. Despite its mysteries, time remains central to our exploration of the universe. From the ticking of atomic clocks to the swirling of galaxies, time connects us to the cosmos, inviting us to ponder its deepest secrets. As science advances, we may one day uncover the true nature of time, a revelation that could redefine our understanding of reality itself. One of the greatest challenges in modern physics is reconciling the conflicting views of time in general relativity and quantum mechanics. Relativity provides a macroscopic understanding of time, showing how it bends, stretches, and warps under the influence of gravity. Quantum mechanics, on the other hand, deals with time at microscopic scales, treating it more as a backdrop for probabilistic events than as an active player in the universe's evolution. To unify these two frameworks, physicists are developing theories of quantum gravity, which aim to describe gravity in the language of quantum mechanics. Among the leading contenders is string theory, which posits that the fundamental building blocks of the universe are not particles, but vibrating strings of energy. In string theory, time might emerge from deeper, more fundamental dimensions of reality. Another promising approach is loop quantum gravity, which suggests that space-time is not a continuous fabric, but a network of discrete, quantized units. In this view, time might arise from the interactions of these fundamental space-time atoms. These theories are still in their infancy, but they hint at a deeper, more intricate nature of time that lies hidden beneath our current understanding. Time is one of the greatest mysteries of existence. From the macroscopic grandeur of relativity to the microscopic strangeness of quantum mechanics, it defies easy definition and resists simple explanations. Is time real, or is it an illusion born of our perceptions? Does it flow like a river, or is it a static dimension we traverse? These questions remain open, inviting us to explore the universe and our place within it. As we gaze into the night sky, we see stars that shine with the light of ages past. Each photon of starlight carries the story of time, its flexibility, its mystery, its interconnectedness with space. Perhaps the true nature of time is beyond human comprehension, a secret woven into the very fabric of existence. But as we continue to unravel its mysteries, one thing is certain. Time connects us to the cosmos in profound and awe-inspiring ways, reminding us of the infinite wonder of the universe.